Good morning. This is, yeah, come in. Yeah, so this is high concurrency table hijinks. My name is Dan Mallott. Talk a little bit more about who I am in a minute. Is everyone having a good morning? Good conference? Yes? No? Maybe? Need more coffee? Yes. Okay. I actually I gave up coffee in January, and I pretty much only drink tea now. So I just had my one tea this morning. Right. So, of course, please make sure that you visit the sponsors. With any event like this, yes, you're paying for your ticket to be here, but the sponsors are allowing us to do a lot of the other things that happen. And without them, either the tickets would be much more expensive or the event wouldn't be able to happen at all. So please go talk to them, check them out. Maybe they can have something that will help you in your job or help you find another job. Right. Who am I? Right. As I said, my name's Dan Mallott. I'm a team lead at Economic. Economic is accounting software based in Denmark. We serve over 180,000 customers in the small and medium-sized business space. And I'm in charge of the platform. So that's the software that runs underneath all of the cool features that people actually get to use. I've been a software developer and occasional DBA since 2011. Somehow I keep bouncing between the two. Primarily, my experiences with Microsoft tech, so C#, .NET, SQL Server, Azure. But my travels have taken me in some other directions, including the four-letter language, which is only how I'll refer to that. And lastly, I referee and play ice hockey. One of the interesting things about moving to Europe is hockey means different things across the continent. Some places it's played on grass, and some places it's played on ice. So I just say, okay, it's ice hockey. Avoid the confusion. I'm also clearly American, so my Polish is very bad, bordering on non-existent. So please, English, if at all possible. Right. So we're going to tell a little bit of a story here of something that happened shortly after I started at my current role. And in that story, we'll talk about, what we got right, what we got wrong, what we got very wrong, and then how we fixed it, and how we are preventing it from happening in the future. Right. So I mentioned Economic is accounting software. It is approximately 25 years old. Like many 25-year-old applications, it started out as classic ASP and database-driven logic. So everything in stored procedures or more likely hard-coded SQL. Thankfully, all that has been excised. Today, it's a modern-ish React.NET SQL Server application. We have some microservices. We have a monolith. We have, some other databases not named SQL Server. We're hosted in Google Cloud Platform, which is nice. It's the first time I've run into somebody who likes GCP. But one of the big challenges that we face in our application, well, there are a couple, but one of the big ones is we've taken this database-driven pattern of we open a transaction, we do some work, and then we commit or roll back the transaction, and we've brought that forward to the modern day. And that's how pretty much everything in the application works from a feature perspective. There's some challenges there. So not every use case involves a database table. It probably didn't 25 years ago either, but there we are. So we have things that we do in the application like sending emails, sending notifications to mobile apps, sending bank transactions. Like we have functionality in our application that allows you to pay your vendor through the application. Okay. And of course, the thing that leads to is if a transaction fails for whatever reason, right? This is the classic explanation of bank transactions that you get when you're learning how a database transaction works. Like you don't want to debit the money if you haven't actually dispensed it from the ATM. Right? So it's the same thing. If the transaction fails or is rolled back for some reason, maybe there's some data missing or it violates an accounting rule. I don't know how a lot of the features work. We don't want to send an email that it succeeded. Or worse, we don't want to initiate a bank transfer that shouldn't be initiated. Denmark is an incredibly digital country, and the whole place still operates on a cash basis, right? Credit isn't really a thing. So there are two main ways we can solve this problem. You can use distributed transactions, otherwise known as a two-part, two-phase commit, or however many phases you need. Or you can implement an outbox pattern. One of those is hard. We didn't choose the hard one. We chose the easier one. So an outbox pattern or transactional outbox, right? When you can't do a distributed transaction, and in our case, it's because we just haven't learned how to do it yet. The solution is to save those messages into a table, put a service external that will actually pull out of that table and then queue to whatever your event bus is, your message bus. Later being ideally, pretty quickly. People like to see the results of whatever they did. Like you don't want to be waiting for your SMS or your email for 10 minutes. This is also really useful if you need to guarantee order. But that's sort of a separate problem. Right, so we did that. And this isn't a bad choice, not at all. So we have our monolith, the thing labeled as economic up there. And when various actions are taken by users or by automated workflows, sometimes that's data coming in, sometimes that's just automated workflows that happen as a result of other things like a receipt being uploaded. We'll send some messages directly to RabbitMQ. That's what we use for our queuing or for our event stream. But most messages get saved to the database. And then we have what we call the outbox processor, because naming things is hard. And it's just a .NET service running in Kubernetes, a couple of replicas, that pulls the database, says, hey, are there any messages that need to be enqueued? And if there are, it will go ahead and enqueue them. It does one other thing that we'll get to. So that's some great history, but it doesn't explain why high concurrency here is a problem. So the volume of messages can be quite high. So I've been keeping an eye on it over the last couple days to get some accurate statistics. We average about 50,000 messages running through that table an hour. I was talking with Matt Gordon, who is sitting in the back corner there. You should go to his session too. It's good. And at 11 o'clock last night, we were still doing 3,000 messages an hour. So, there's some decent volume, right, running through this table. And when we started, each instance of the outbox processor would process a single message at a time, which is entirely reasonable, right? There's really lightweight logic. The only thing we did between pulling it out of the database and putting it onto Rabbit was making sure that we could deserialize the message. And the reason we did that is so that that didn't have to be implemented on the consumer end. We wanted to assure once and only once sending. So distributed systems are hard. So essentially, the outbox processor would open a transaction, delete the message while reading the deleted contents. In that open transaction, do its deserialization, queue it to Rabbit, and then commit the transaction, or roll it back if something went wrong. Each time there was nothing to do, it would try to get another record immediately. And in times of high volume, one member of the team would manually scale the microservice out to improve throughput, or back in. But basically, he would sit there in the interface and just go, okay, well, I think 7 will do it now. No, maybe 5. Who can tell me what the first issue was? Yeah, aside from the guy manually scaling it, like, it's 2023, what are we doing? So we had a small problem with deadlocks, right? So we have 100 instances of our monolith inserting to this table. Meanwhile, we have 5 to 10 to 15 instances of our consuming service locking the table, well, opening a transaction, deleting a row from the table, doing a little bit of stuff, and then committing the transaction. Yeah. So we had a bit of a problem. This was our first hint that we had a problem, or should have been. This was just sort of accepted as like, yeah, this is okay. This is the state of affairs. We'd actually had a consultant come in prior to when I started, who tuned it to be this performant. And at peak times, we would wait for over an hour sometimes for messages to be delivered. So that's not a great customer experience. Pro tip. Right. So shortly after I started, I said, hey, maybe we ought to try to fix this a bit. Like, this seems like it might be a problem. So right, how do you address deadlocks, right? So it's a super high concurrency table. Our first problem is deadlocks. And we kind of took a naive approach. We first reduced the simultaneous queries. So remember how I said that every time it didn't have something to do, it would immediately hit the database to try to get something to do, right? And so you had all of these workers locking the database simultaneously. So we introduced a staggered backoff, so it would randomly wait a bit to try again. So that at least the workers weren't contending with each other when the queue started to fill up again. I'll talk a little bit about why that didn't work as well as people thought it would. And the other thing is we dropped the number of workers. Fewer things trying to get a lock on the table, less chance that you're going to have a problem. There's one other thing that we'll talk about, right? Oh, and we added a lot of monitoring. So one of the things that we had already established was a monitor around queue depth. And observability is really important. So we knew when the queue was starting to build up. But we added other metrics, and we created a dashboard. So cycle time, SQL errors, so like we knew if the number of deadlocks started to climb, right? And unfortunately, at the time, this was only based on an application perspective, right? We only knew when deadlocks were climbing when we saw exceptions coming from .NET. And then we set some thresholds for alerts so that we could react quicker. And this kind of worked for a month. There's a bigger version of this. I'll show what this looks like today. But this was a screenshot I took last week, and you can see we were 72,000 records in an hour. Right. As I mentioned, this seemed to stabilize things, but it was kind of a false hope because in accounting, like in many businesses, activity is cyclical. So yeah, until it didn't. There was one other thing that I didn't put on a slide, but was really important to know. So our monolith, which is the core of the application code that we have, some of the code is 20 years old now, dates back to the original ASP.NET web forms. All the classic ASP is gone, but there's still some real old stuff. Is very, very difficult to change. We have a lot of change management around it for audit purposes, and we just didn't want to mess with it because it's hard to get things out the door quickly. Oh, and there's a custom ORM, which, to my surprise, was not the cause of all of this. Yeah. Didn't fix it. Actually had no chance when we looked at it in retrospect. Like we were like, oh yeah, all the deadlocks are gone. Like we're not seeing, like we're having reasonable queue length. Like queue's not getting too bad. Too bad. Yeah. And then we had some bigger problems. So, as I mentioned, we're accounting software. As you might imagine, the first business day of a month, very busy for accountants. Right? You're closing the previous month, at least in Denmark. Most of your bills are paid on the first of the month. And when it's the first business day of a quarter, it's even busier. And the guy who was doing the manual scaling, he was on vacation. And unavailable. As a team lead, I really live and die by, if you're on vacation, I'm not calling you. In this case, I literally couldn't. Yeah. So we got an alarm at 9:45 a.m. Said, hey, the queue is really starting to grow. It's over, I think it was over 20,000 at that point. You might want to do something about this. And so our alerts trigger into Slack, and they tag the team that is responsible for fixing it. So it's quite nice. So we scaled it up to 15 replicas. Little did we know that at the same time, the CPU load on the server was spiking. And our site reliability engineering team, who's responsible for taking care of the SQL Server, started seeing CX packet weights, just like super high CPU usage, like it was maxed out 100%. And they monitored the whole application. They were starting to see wait times on our website, the web application, of over 5 seconds for requests. That's bad. Now, the good news is we knew it was happening before our support people reached out. The bad news is our support people had to reach out. So we scaled it down. First time to 10, and then to 5. It took about 3 hours for the CPU load to clear. And then we were allowed to scale back up. And we didn't, the queue topped out. I want to say I didn't capture pictures at this time because I was like firefighting, right? When you're firefighting, you don't think to like, oh, I need to take a picture of this thing that's burning. But we were up over like 1.5 million notifications in the queue that hadn't been sent at one point. We finally cleared it a little bit after 8 p.m. But we had messages that were delayed by over 4 hours. Which, if it's an automated notification or a bank transfer, like that's generally okay. Emails, people getting set up with new accounts, that's very bad. This was all very bad. And it was very bad because then we had to do it again the next day, and we knew that was going to happen. Yeah. One does not simply recover from disaster, unfortunately. So we had already done our quarterly planning. I amended our team's quarterly plan to say, hey, we need to fix this thing. We really need to fix this thing. So how did we do that? And this is where we started unpacking all of the turns where we had gone wrong. So we started taking a deeper look at what was going wrong. The biggest contributor to this was that no one really understood the locking behavior of delete statements in SQL Server. So previous developers had added a read past hint, and that was initially presented to me as like, well, this can't be it because it's reading past the row that it's deleting. And I said, I don't think that sounds right. But at the moment it worked until it didn't. So when you delete a record, SQL Server takes out what's called an intent exclusive lock on the table. And this lock says, I intend exclusively to remove a row. But what that does is when you're doing, as we were, delete top one with no where clause, that escalates to an entire table lock. For reason that I'll get to in bullet number 3, if you want to read ahead. And so this was just an incredible performance sink. Like, even when it didn't deadlock, it was very, very slow to get records out of the database. Like, we're talking over a second sometimes. Interestingly enough, because we're in read committed isolation, or sorry, repeatable read isolation, the inserts were fine. They were never blocked. In addition, the outbox processor was deserializing the message. Now, doing string operations in code is never going to be the fastest thing. When it was originally developed, the messages were fairly small. We see average message sizes of about 1 kilobyte, which is a lot of data to deserialize while you're holding a transaction against a table. And probably the cardinal sin, that the table itself was a heap. Now, if you have a table that you are just wanting to insert as efficiently as possible to, and you never care about getting the data out again, or you do care, but it's not a performance critical thing, a heap is a great choice. If you have a table that is reading and writing a lot of data, that's not good. Because the inserting is still going to be fine, but anytime you need to get something out, now we're going to do a lot more work. Because we don't have a clustered index to just go, I'm going to take the first record off this clustered index. Yeah. Oh, and there were no indexes on the table either. None. It was a heap with not even a non-clustered index on it. Gotta love it. So what we did is we applied some fixes. Yeah, so the first thing we did was we converted the table to have a clustered index and a primary key. And as I was reviewing what we had done, we also increased the table from being an int to a big int identity. It had an identity column. Like it just anyway. And that actually improved things measurably, but we were still seeing deadlocks in our testing. So how many people in here have a testing environment? Good. How many people in here have a dedicated production environment that's not the testing environment? Yeah. So we're fortunate. We have, I think at last count, it's 14 acceptance environments. And we have full sets of services with each of those. So we took one of those, we had fewer then, but we took one of those acceptance environments out of rotation. So ordinarily we allow developers to, it's complicated. We don't need to talk about that. But we took an acceptance environment and said, okay, we're going to do some testing here. And we're gonna really hammer this to make sure that we've gotten it right. Oh yeah, and our acceptance environments at the time had full scrambled, anonymized copies of the production database, which is really important. They don't anymore because our cloud bill was insane. Right. So changing to the clustered index solved some of the performance problems, but we still really couldn't scale. And if we really hit the table with a lot of records, the processor itself couldn't recover. It pretty much just, like the queue would just continue to grow, the queue table. So sort of got to a place where, like, I don't think the answer is SQL. Like, I don't think we're going to SQL our way out of this. Well, entirely. So we looked at what we were doing. We said, okay, we're opening a transaction, we're deleting a record, and then we're closing a transaction. What if we didn't have to hold that transaction open while we were doing all the stuff with the record? So, fun story. There was already a processed column on this database, on this table. So somebody at some point in time thought, hey, maybe we can just mark these as processed. And so what we did was we added a processing column. Like, hey, we are working with this record. And then we added a filtered index. Because we wanted to make sure that getting things that were not processing and were not processed was really, really as fast as it could be, right? And then we re-architected the microservice. So we first got records, a configurable number of records. We updated them as being processing. We deserialized them. It turns out that wasn't a performance issue as much as we thought it was. Not that we haven't tried to improve that since. We enqueued them to Rabbit, and then we updated as processed, or not if there was a queuing failure. And then we added a process to clean up the table later when there was less load. And I mentioned we added a way to get more than one record, so we configured it. We added configuration, say, okay, I want 10 records. We could configure it up to whatever maximum int is. We started at 10 in a loop. Because it turned out in our scenario, so you remember when I was talking about when the outbox pattern is really good is, like if you need to ensure order. We didn't. Order was not important. So we parallelized the processing. Said, okay, we've got a lot of extra CPU capacity in our Kubernetes cluster. Let's take some pressure off of SQL and do more things at the same time. And then we monitor it more. Now, the really hard thing is our synthetic tests, which we were doing in our staging environment, were just synthetic tests. We didn't have the ability to capture a true production workload. We have since, because we're in the midst of doing a fun 2016 to 2022 upgrade. Fun. But the synthetic tests, we monitored it. We said, okay, this looks good, or this is at least looking better. We had no more deadlocks. We had no more random CPU spikes, at least not coming from us. CX packet was way, way down. And we rolled it out to production. And kind of held our breath at the beginning of the next month. And then we applied some more fixes. How many of you have had the pleasure of working on one of those, we're rewriting the core functionality of an application while it's running in production? I refer to it as changing the engines on the airplane while you're in the air. Yeah. Sometimes you forget to attach an engine. So we saw what happened at the beginning of the next month. It actually was pretty good. Honestly, we got it nearly right on the first try, which was surprising. But there were some holes. So we noticed that we were getting messages stuck in the processing state. We also were having random errors being thrown that we couldn't enqueue to Rabbit because the connection was closed. As it turned out, when we scaled the microservice, it wasn't shutting down cleanly. Oops. So we did two things. We added a clean shutdown, and we added a retry policy. We removed the random backoff. We did this after talking with the SRE team to make sure that we weren't about to destroy our SQL server. And they gave us the blessing and said it's fine. And then, in a more complicated thing, we implemented horizontal auto scaling based on the queue size. So in the container world, you can scale vertically or horizontally. Like vertically is you add more resources, horizontally you add more machines. In this case, we said, well, if we have more queue depth, more items in the queue, let's add more pods so that we can churn through that queue quicker. And this is something that we were able to do because of our observability tool. We were able to use the metrics that Datadog is what we use, that Datadog was giving us to do this scaling. And then most importantly, we implemented SLOs, so service level objectives, on the size of the queue, the time to deliver messages, and the query latency, most importantly. Because we wanted to make sure that if this started to crop up again, we would know. So what were the results? So I set our SLOs long before we knew what the end results were. So our processing time SLO, so that's how long it takes from a record hitting our table, hitting that outbox table to being in queued to Rabbit at 120 seconds. In reality, I don't think I've seen it go above 10 seconds in months, and it's usually in the 2 to 3 second, or when I looked this morning, sub-second range. We'll take a look in a second. The database contention was almost entirely eliminated. I say almost because we are still seeing it, but we're not sure whether it's from us, from this use case, or from something else in the application. There are lots of people opening transactions, doing things, and then committing them. Sometimes opening a transaction, opening a nested transaction, opening another nested transaction, and then unwinding that. And service scaling, we're usually sitting at one replica, but we scale in response to system needs. And by doing that, we've actually been able to drop the cost attributed to this service quite a bit. At least we aren't sitting there with 10 giant services running. Usually it's one. We'll probably, when I swap over to the dashboard, we'll probably see something interesting. Yeah, let me do that. Yeah, so this is our dashboard, and take a little walk. And so you can see, kind of importantly, the important things here, right? So we have our queue depth, we have the latency on our SQL query, and so we look at it by a lot of different breakdowns. So not just what's the median, but what's our P99. Most importantly for us, what's our P50 today and yesterday. But you can see, like, that's pretty decent. Something must have happened yesterday that jumped that up. Max wait time, the number of pods, and how many messages we're seeing. Right smack in the middle, and most importantly to our customers, no message failures. Yeah, so I mentioned that when the incident happened, this was last October, we took a look in an organized fashion afterwards. And, in addition to all of the observability and like what you should look for, post-mortem is really important. Specifically, it helped us understand where the issue was, right? Because in preparing for that post-mortem meeting, we actually had to do research about, the history. Why does the application look the way it looks today? How is it architected? What is it doing under the hood? Not just like this happened. Importantly, we were able to review the incident in a lower stress forum. So rather than in the heat of the moment where everybody's going, fix it, fix it, fix it, say, okay, here's what happened. Here's our timeline. This is what we got from my team, from the SRE team, from our support folks. We have about 300 folks sitting on our floor who their only job is phone and chat support with our users. We know immediately if something is wrong. Like, our challenge is to know before. And then because we had those diverse viewpoints, we were able to openly discuss different strategies for fixing the issue, and we could debate the merits of each. Most importantly, blameless. Sometimes it's somebody's fault. What's that saying? Success has 1,000 fathers and failure is an orphan. Sometimes failure is, sometimes you can identify who screwed something up. In our case, we knew who screwed it up, but they weren't there anymore. But even within that, we didn't blame them for what was done. We took the approach, what was done was done. We can only move forward, which is how you get people comfortable to fix things and take chances fixing things. So what did we learn? So our key lessons. Heaps are very bad in heavy read-write scenarios. As an aside to this incident, our chief architect took a swing through the database and found at least 3 other places where there was a heap in place and it shouldn't have been. And he was a bit upset by that. Table hints don't override locking behavior. Now, how many people in here use query hints on a regular basis? Got a couple. Okay. I'll say something only very slightly controversial. Table hints are a code smell. But there are use cases for them. Right? So a good example of a code smell, our custom ORM, God help it, appends with no lock on every query. Joey back there said it's only financial data. Even better, we're in repeatable read. You know what that no lock hint does? Nothing. Does nothing. Ironically, so we learned table hints don't override locking behavior. And yet in the solution, I can't share code, unfortunately. Economic and Visma as a whole have very strong IP policies. I actually use query hints, but not just read past. The third thing we learned, and this can be challenging when you first start going down a really deep observability path. Logging and monitoring are only going to tell you that you have a problem. They aren't going to tell you what the problem is or where it came from. Right? Like our SQL Server monitoring has come a very, very long way. But it can only tell us that we're seeing weights, increased weights, or increased CPU. It can't tell us where it's coming from. And less can sometimes be a whole lot more when concurrency is involved, right? That's all I have. I have time for questions, if there are questions to be had. Erlen.
Well, the obvious one is, yeah, I'm not saying that you don't need to go back and read this item. You heard about service problems?
Yeah, so for those of you listening online, Erlen's question is, have we heard about Service Broker? I have. The reason why it's been chosen not to be used is one, the architecture team went for something that was best in class. I'm putting that in quotes, and chose Rabbit. The other reason is that in the roadmap, long term, we are looking to try to move workloads off of SQL Server so that we can drop our licensing costs. Sorry, Microsoft, I'm sure you're listening. I'm not actually sure that if we were using Service Broker in this case that it wouldn't have exacerbated the problem that we saw. The ultimate problem was the high CPU usage. Something to play around with, I guess. Any other questions? Yeah. Yeah, so the question is, why did we involve the database in this at all? Why not just send the message right to Rabbit? Which is a question I asked when I first got there. Why do we even have this? So essentially, because of the way we've gotten used to developing the application, people open a transaction, do a lot of work, and then commit the transaction or roll back. We didn't want to, we wanted the sending of the message to be part of that transaction. You can debate the merits, and I have with a few people, but that was essentially, it was the easiest solution for our feature developers to handle, was that we would give you a service in code that if you were in a transaction, it saved it to the database table, and you didn't have to worry about handling it after you were done. I'm not going to claim that makes a lot of sense, but that's the history. Other questions? Okay. Okay. We have flexibility for the future. Thank you all.